Welcome back to another Daishinfinity video. In this video, we're going to prove the derivative of cotangent hyperbolic, which states that the derivative of this function is equal to the negative of cosecant hyperbolic squared of x. So in order to prove this, we have to use the limit definition for the derivative. So in order to find the limit definition, we have that the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Now, cotangent of hyperbolic of x is equal to the cosh of x divided by the sinh of x. Now, with the help of Euler, we can demonstrate those two functions with using the exponential function e to the x. So we can state that the cosh of x is equal to e to the x plus e to the negative x over 2, the whole thing over e to the x negative e to the negative x over 2. So we have the 2's are cancelled out, and we have cotangent hyperbolic of x is equal to e to the x plus e to the negative x over e to the x negative e to the negative x. So if we use this, we can use this exponential function demonstration in order to put this in the limit and then try to find what is coming out of the limit. So the derivative of cotangent hyperbolic of x is equal to the limit as h approaches 0 of e to the x plus h plus e to the negative x negative h over e to the x plus h negative e to the negative x minus h, and the whole thing minus e to the x plus e to the negative x over e to the x minus e to the negative x over h. So now we cross multiply and we get this thing, and we have to just group the two parentheses here, Roman numeral 1 and Roman numeral 2. So we just distributed this and we get e to the 2x plus h minus e to the h plus e to the negative h minus e to the negative 2x minus h. For the second Roman numeral, we have those two parentheses, and by distributing those two parentheses, we get minus e to the 2x plus h. The minus sign is from the limit definition, and then we have plus e to the h minus e to the negative h minus e to the negative 2x minus h. So if we distribute the minus sign again, we have the negative e to the 2x plus h, negative e to the h plus e to the negative h plus e to the negative 2x minus h. So we have to combine those two, and we get e to the 2x plus h minus e to the h plus e to the negative h minus e to the negative 2x minus h minus e to the 2x plus h minus e to the h plus e to the negative h plus e to the negative 2x minus h. So those things cancel out, and we get 2e to the negative h minus 2e to the h. Now at the last part, so we have just simplified the numerator. We are just going to try and solve this limit with the simplified numerator. So we have the limit as h approaches 0 of 2 times e to the negative h minus e to the h over h times e to the x plus h minus e to the negative x minus h times e to the x minus e to the negative x. So the 2 and the e to the x minus e to the negative x is all independent of h, so we are just going to put them outside of the limit, and then we get 2 divided by e to the x minus e to the negative x times the limit as h approaches 0 of e to the negative h minus e to the h over h, and then also times e to the x plus h plus e to the negative x minus h. Now, if we plug in the h's inside of this limit, we would have 0 over 0 situation, so we would have to try and simplify this again. And since we can simplify e to the x plus h minus e to the negative minus h, we can split this limit into two using the limit principles. It states that the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x, which is also equal to f of a times g of a. So we are just going to separate those two, and then we get 2 divided by e to the x minus e to the negative x times the limit as h approaches 0 of e to the negative x minus e to the h divided by h times the limit as h approaches 0 of 1 over e to the x plus h minus e to the negative x minus h. So the h's will approach 0, and we have 1 over e to the x minus e to the negative x, which is just equal to the other denominator, which was already outside of the limit. So we get 2 divided by e to the x minus e to the negative x squared times the limit as h approaches 0 of this whole chunk. Now, if we plug in h is equal to 0 or approaching 0, it will go to 0 over 0 situation. So we can use the L'Hopital's rule to differentiate both parts of the fraction. So we will get negative e to the negative h minus e to the h over 1. So now if we plug in the h is equal to 0, this will approach 1 and the other one will also approach 1, which will equal to negative 2 because we have negative 1, and then we have negative 2 times 2, which is equal to negative 4, and the result will be negative 4 over e to the x minus e to the negative x squared. Now everyone would ask themselves, okay, where do we get the cosecant hyperbolic squared of x? Now we know the sinh of x is equal to e to the x minus e to the negative x over 2. But if we flip this, we get cosecant hyperbolic, and if we square it, we get 4 divided by e to the x minus e to the negative x squared. And we have negative 4, so we just have to multiply everything by negative 1 in order to get our final conclusion that minus 4 divided by e to the x minus e to the negative x squared is equal to negative cosecant hyperbolic squared of x. So now we can state that the derivative of cotangent hyperbolic of x is equal to negative cosecant hyperbolic squared of x. I hope you liked this video. Please like and subscribe, comment if you have any questions, and we'll see us in the next Daishinfinity video. See ya.